What?
Charge, like, is it going to run out of batteries?
Yeah, it'll be fine. Welcome to Linear Algebra Lecture, I think number 6. The last one! Woo! Two main topics for today. First, we're going to do wedge products. When you do integrals and you have that little bit at the end, that's like dx, dy, dz, that thing is secretly a wedge product. After that, we're going to talk about how various function operations map to various matrix operations, and that'll sort of give us a way of contextualizing a bunch of the stuff that we've talked about in the previous lectures. So, wedge products. We'll start with use cases. So normally when you're like doing integrals, you don't really need to worry about exactly what the dx and dy and dz at the end are, right? There's sort of those variables floating around at the end, and the sort of case where it starts to get complicated is like, for instance, maybe you have some sort of surface and there's something flowing through it. So, for instance, maybe you're doing a fluid mechanics problem and there's some fluid flowing through this surface, or maybe you're doing an electrodynamics problem and there's an electric field or a magnetic field. You want to look at its flux through a surface. This was a bad arrow. And you want to like calculate how much fluid is flowing through the surface, or how much electric or magnetic field is flowing through the surface, that sort of thing. If so, in the simple cases, you have a conserved flow where, like, for instance, if you have some water flowing through a surface, probably you don't have like little point sources of water all over the place. You probably just have one source of water up the pipe, and the amount of water is conserved as it flows through whatever this is. And then it's pretty easy, because like if you move the surface a bit, the total amount of fluid flowing through won't change. So in that case, you can sort of pick a relatively easy surface and avoid most of the difficult stuff that way. But it's a lot more difficult if, for instance, you have sources in the body here. For instance, maybe you're dealing with some sort of magnetic problem and you're trying to calculate magnetic flux. You've got like magnetic sources sitting inside of some other fluid, and then it's going to get real. You're not going to be able to like move around like that. Or maybe you have some like particular surface within a larger systems. Like maybe here's your tube, and you just want to know the flow through this surface, not like the whole tube. Then it's potentially more difficult. That sort of thing. You could also be in like higher dimensions. Maybe this is like an n-1 dimensional surface. Welcome. n-1 dimensional surface in n dimensions. You could have really funky stuff, like maybe I have a sphere, and on this sphere I have some flow on the surface of the sphere, not through the sphere, but on the surface of the sphere. And then I have a curve on the sphere's surface, and I want to calculate the flow through that curve on the sphere surface, right? So these are the sort of like geometric problems or geometric flow problems where like you need like some somewhat more sophisticated machinery for talking about, for instance, what your little dx, dy, and dz are. Like in this case, your little dx and dy and dz might be like the area of this little curved patch of surface here. Or how do I talk about the area of this patch of a curve on the surface of a sphere, right? Especially in the case where like you're in n dimensions. So in fact, this is like an n-2 dimensional surface. We're trying to talk about something like an area of that thing, right? This is where wedge products can be really handy. So, basic idea. If I write something like dx dy, usually in an integral, this thing is secretly a wedge product, so what it actually is wedge dy, right, like that. Or maybe there's dz in there too, so you get like dx, dy, dz. First key thing is that this is like conceptually a measure of volume. So like intuitively, as you'd expect from calculus, like you sort of think this thing is a little tiny unit volume, right? And that carries over. But first of all, it may be like have some weird dimensions to it. So for instance, if I'm in 3 dimensions and I have a dx, dy, dz, then dx dy is like a little surface area, right? It's oriented. So in the case of dx dy, it's like, let's say, here's my x direction, here's my y direction, and my z direction is out of the board. Then my dx dy is saying like, it's like a little square like that, right? And it's oriented along like the x and y direction. Then once I take the dz, then it becomes the unit volume. Right?
Is this the geometric algebra that Alok and Scott really like?
Very nearly, yes.
Okay.
Geometric algebra adds like one additional piece to this, but this is the core part of it. Yeah, so you can think of these guys as like little volume or area elements. They are signed, so there's a difference between dx wedge dy minus dx wedge dy. Roughly speaking, this corresponds to if you're thinking about it as like an element of a surface, it's whether you're looking out through the surface or looking in through the surface. So, for instance, in that case from before, where I was thinking about an integral flow through a surface, one of those would be taking flow outwards, one of them would be taking flow inwards, and the sign flips if you swap the order of things. So dx wedge dy is minus dy wedge dx. That's the main sort of weird and counterintuitive thing about wedge products, and sort of where most of their structure comes from, is this anti-symmetry.
That doesn't seem counterintuitive to me.
Yeah, once you know that like it's signed, it makes sense, right? Because like I have my little area element that's a dx and a dy. If I think about swapping the dx and dy, then now instead of like sort of thinking about it going this way, it's going that way. Right? So it's a sign change. I've flipped which side is inside, which side is outside. Some other properties. Start from that. Actually, some general properties. Which product is linear? That's nice. So, in particular, when I'm doing coordinate transformations, say I have some other coordinates a, b, c, then I would typically say something like dx equals partial x partial a dA plus partial x partial b dB plus partial x partial c dc, right? I can still do that. These things work like differential elements, just like you're used to, so this totally still applies. And when I take my wedge product with dy, I'll now have dx wedge dy is equal to partial x partial a dA plus partial x partial b dB x c c wedge dy. And linearity, that means I can like distribute that dy out. This will be equal to partial x partial a dA wedge dy plus yada yada. Two terms, right? So intuitively, that's gonna work roughly the way you expect. An important thing that comes from anti-symmetry here is if you take anything wedged with itself. So like, for instance, dz wedge dz, that has to equal minus dz wedge dz, and therefore it equals 0. Does that make sense? So intuitively, that's saying, look, if I'm taking the area of like a little element, both of my arrows are in the same direction, that has area 0. So that will allow us to simplify a lot of stuff when we do these sorts of coordinate transformations. So write that out right here. I also have a dy here. I'm going to get rid of the c for a minute. Write less. So if I have both an x and a y, and I'm substituting in doing a coordinate transformation for both of them, then my wedge is going to look like this. Partial y, partial a, dA, plus partial y, b, b. Okay? So I'm going to get a dA wedge dA term. That's going to be 0. A dB wedge dB term. That's going to be 0. Here I'll get a dB wedge dA term. So that'll give me partial x, partial b, partial y, partial a, dB wedge dA. And then my other term is going to be a dA wedge dB. So partial x, partial a, partial y, partial B, dA wedge dB, and then dB wedge dA and dA wedge dB are negatives of each other. So this is going to simplify down to partial x, partial b, partial y, partial a, minus partial x, a, y, partial b, times dA wedge dB.
That would be dB wedge dA.
Sorry, what?
That's dB wedge dA.
Oh, it is dB wedge dA. Oh, good. I was wondering why things were backwards. Thank you. In that case, put the minus sign over there and make it dA. Much better.
Success.
Yeah, all right. That makes me happier because that makes this next bit a little cleaner. Anybody recognize that guy right there?
Is it like the chain rule or something?
I feel like it's related to torque.
I'll give you a hint. There's going to be a matrix involved, this being linear algebra.
Ooh.
This is a determinant of, so this term would be
Jacobi.
partial x, partial a. This term would be partial y, partial b. That's those two. Then minus partial x, partial b, partial y, a. So yes, this is the Jacobian of the xy coordinates with respect to the ab coordinates. And you take the
Whoa.
determinant. So back in multivariate calc or whatever, you may have learned that when you do a coordinate transformation on something like dx, dy, dz to a dA, dB, dc, you pick up an extra term here, which is the determinant of the Jacobian of x, y, z with respect to ABC. That's where this comes from. So if you take a wedge product of n elements, and you've got n wedges. So in this case, we're taking a wedge of two things, and we had it was a 2 by 2, right? We're going from these two variables to those two variables. That always works out to be a determinant. Yeah, and in fact, that's one way to think about what a determinant is. But the wedge product is also more general. So in this case, it's like you're doing a full coordinate transformation from like all three of these coordinates to all three of those coordinates. You could also imagine doing something like a partial coordinate transformation, where like we're going to transform x and y into something in terms of a and b and c, and then we'll just have an expression for dx wedge dy, and that'll become an expression that'll have three terms in it. It'll have a dA wedge dB, a dB wedge dC, and a dA wedge dC.
Mm-hmm.
So it'll have like all the pairs, and you'll have a sum of terms like that. So that's the sort of thing that happens when you do wedge products. So far, so good. Questions? Yeah. How are we doing on time?
It is 7:15.
Great. Going pretty quick. I think if I want to do we want to do like a full example of this? A non-trivial example. All right. Sydney says yes.
Yes, but I am one of three.
It's okay. I think we can examine it. So there was this problem we did back in E&M where like you have something shaped like an ice cream cone. So there's like a half dome on top and then a cone on the bottom. And then I go stick a point charge right there, or like at some point inside of this thing. And I want to know how much of the electric field flux goes out through the cone versus the dome.
Ooh.
I've seen this.
If you've taken an E&M class, you've probably done something like this at some point. Yeah. I'm probably not going to go through this whole problem because the math there's some gnarly algebra in there, but we can talk about like conceptually how to go about it. So first we're like sitting in space. Let's call this one the z direction. We'll assume that like the axis is at x equals 0, y equals 0. Okay. So it's symmetric about the z-axis. And then how would we parameterize like a little surface element on this half sphere? And how would we parameterize a little surface element on this cone?
I have two dumb questions.
Yes.
one, are we trying to find the ratio of like how much goes out through the like dome versus the cone?
Sure.
Can't we just look at the like split of like the circle that it has to go through that decides whether it's going to go out through the cone or through the dome?
Yep, that's exactly right. So
Okay.
because the electric field is conserved anywhere there's not a point charge, one clever way to do this would be to say, let's look at this circle right here. The flux is either going to go through this circle or through the cone surface. So instead of integrating over this whole half sphere, I could instead integrate over that circle. And probably I could even further simplify, like for instance.
Don't I cannot worry about the like? Isn't all of it just like going out of the cone just gonna be the rest of it or something?
Correct, yes. So you know how much flux is coming off the charge, therefore you could just do this surface or just do the cone. Yep, that's right. Yeah, this is the sort of clever solution that you're supposed to think of when you're doing this sort of thing in physics.
But we like hard work.
You know, it's important to know how to do it the hard way.
Okay.
Because every now and then you run into something where the clever trick isn't going to work.
Okay.
Or you need to tell a computer how to do it.
Or that, yeah. If you can tell a computer how to do it, that like totally counts. You're good. So anyway, so we want to integrate.
Oh no, I mean you would tell the computer how to do it the hard way, and that's why the hard way is good.
Oh yeah, that also works. All right. So let's think about what would the integral look like. So you have you're going to be integrating over a surface for both the cone and the sphere. How do we want to parameterize the cone and the sphere? Let's pick one. Do we want to do the cone or the sphere?
Sphere.
Sphere. All right. We're going to do the half sphere. How do we want to parameterize it?
First parameterize it in terms of the sphere, and then parameterize the terms of the sphere in terms of the x, y, z.
I meant more in terms of like a coordinate system on the sphere.
Oh, just use the center of the sphere, which is going to be on the circle.
That's also not the question I was asking. Yes.
I mean, I haven't done enough math in a long time, but I'm like, I don't know. You could either parameterize it in like whatever spherically coordinates or in like whatever.
Circly coordinates. Those sound
Circly
promising.
coordinates, yeah.
Yeah.
Oh,
all
yeah.
right.
The this thing and then the that thing.
Yeah, the this thing and then the that thing. That's it. Yeah.
I mean,
all right. So we've got how about a thing that away and then a thing. Well, I guess usually go down from this axis, like that, and then one of those is going to be theta. One of them is going to be phi.
I think this is
Yeah.
phi, and
Remember
then that
which of
one
those
is
is
theta.
which.
This one is phi.
Move your arm again.
Oh.
That one's phi.
Yeah.
All right. Call that one phi, and then the other one is theta. Yeah. All right. So we've got a phi and a theta here. Do we remember how to relate those to x and y and z?
Probably involves a cosine or something.
Probably involves a cosine. Yeah, that
That's
sounds pretty
nice.
accurate. So I'm gonna guess. Yeah. Like
Phi is going to be sine, and then theta is going to be both.
Oh, yeah, that sounds right. But I don't.
so I'm gonna do the easy part.
Well,
There's definitely an r in there. All right. I'm gonna guess that x has a cosine theta, y has a sine theta, and then z, I'm guessing doesn't have any theta,
it's going to have.
like a cosine
Yeah, it won't have a
phi,
theta.
and that would imply a sine phi, something like that.
This rings a bell, but I wouldn't know if it's wrong.
Looks vaguely plausible. I'm not really
Yeah,
convinced,
that looks
but
right.
vaguely plausible. All right, great. That's progress. So this means we can get relationships between like dx, dy, and dz wedges and d theta, d phi wedges, right? So that's nice.
Oh,
Look,
Just gonna do a thing in the corner.
Yeah, go ahead.
Who is this recording shared with?
YouTube.
The whole of YouTube?
Yeah. You can do a thing in that corner, that corner. All right. So yeah, what about our surface elements? We need like some surface areas here. How are we gonna get those?
The surface area is going to be dx, dy, dz.
That's a volume.
Wait,
dx, dy, dz. That's,
Oh, yeah.
that's like a volume element. Just
Oh,
dx,
it's-
dy.
no, it's going to be d phi d theta. d theta.
All right, let's talk about d phi. D
Right.
theta.
Oh, or maybe there's gonna be.
You're on the you're in the right ballpark.
I think there's a sign there.
Let's say d theta d phi. Yeah. So
I think you'll have to add a sine phi.
we'll get to that.
Okay.
First, let's talk about this guy. So d theta d phi. That thing has the right shape to be a surface element on here. You'll probably need to multiply by an r and maybe a sine of something, but has roughly the right shape. So now let's say I want to express this in terms of dx, dy, and dz. Do that.
Substitute.
Substitute. Great. All right. So I've got dx is equal to big R times, I guess that would be a minus sine theta sine phi d theta plus r cosine theta cosine phi d phi. Yeah, someone yell at me if I'm doing my math bad here. All the people on YouTube will fast forward past this.
Nope. I am saying now they cannot.
You're telling the people on YouTube to not fast forward. All right, YouTube people. Garrett says don't fast forward. You're not allowed to. You take it up with Garrett. All right. So I've just done all this lovely algebra. So if I want to, solve that. You all look so excited to solve that.
Oh, that.
Yeah, that doesn't look like quite the right shape, does it? I'm gonna handle that.
What do you mean it doesn't look like the right shape?
Well, how am I supposed to get to solve these for d theta and d phi?
Well, the last one gives you d phi.
Well, last one let me express d phi in terms of dz.
Oh, but
So
not.
I could then substitute that in here, but then I've got two equations for d theta, which sounds like trouble. I don't like having two equations for only one unknown, especially when the only one unknown is only one dimension. Thoughts?
Is the concern here that it's going to be overdetermined and there may not be a unique answer?
Yeah. Why would this not be overdetermined? How do we get around that? I'll give you a hint. Picture what we're talking about here. You've got a little surface element, d phi, d theta. What dx, dy, dz generate that?
Triangles?
Key here is you need to have dx, dy, and dz all stay within the local plane. Like if dx, dy, dz go off the surface of this sphere, then you're no longer going to be able to express those in terms of a d theta and a d phi.
Oh, so there's some
one of the-
relationship between the dx and dy's.
There you
It's
go.
a linear relationship.
It's
Yeah.
The constraint we have to always satisfy here is x squared plus y squared
Non-linear.
plus z squared equals r squared. Therefore, 2 x dx plus 2y plus 2z dz has to be equal to 0. And I believe we should find that as long as we satisfy this equation, then these equations are solvable for theta and phi.
Mm.
Make sense?
So you back out a d theta, d phi out of those three plus this last one.
Yep.
And then we write our integral.
Yes, and now we can express our d theta, d phi in terms of, we can pick any two of x, y, and z. So essentially we're switching to a parameterization where we're parameterizing the surface in terms of x and y, or y and z, or x and z.
Shouldn't this not, shouldn't, the center of the cone is not on the 0. So
Well,
in this case, there's
hang
going to
on.
be, it's going to equal.
I can solve this. There,
Okay.
I'll solve. Right, where were we?
We can solve them given we have that constraint satisfied.
Good. All right, progress. Now, someone was mentioning earlier that we're going to need a couple of other terms here, not just d theta, d phi, but also r, I think a sine of phi. Not 100% that's it, but folks on YouTube can look it up later. It's either a sine or a cosine of phi or theta in there. Right.
I think it's sine phi because phi's the weird one, and I remember being weirded out by it.
Well, yeah. Anyway, yeah. So there's some other stuff in here in order to get the right like volume element there. That's the thing you go look up. Back to the textbook. The important thing is this lets us convert between like these theta phi coordinates and xyz coordinates without having to write them as like square root or sorry, not square root, inverse tangent of horrible expression, right? So we can like do ordinary algebra on relatively clean equations, not have to suffer too terribly. Okay, that was the main point I wanted to make with these. Make sense?
Yep.
Cool. All right. I declare that enough wedge products. On to the second bit. This is sort of the wrap up for the lecture series. So high level idea is there's generally a mapping between function operations and corresponding operations on matrices or like linear algebra operators or whatever. So for instance, a relatively simple one. What's one thing you can do with functions?
Compose.
Compose them. Great. So I have two functions, f and g. I take f of g of x. It's composition. What's the corresponding matrix operation?
Multiplication.
Multiplication. Why?
Because matrices are linear transformations.
Because when I differentiate, chain rule gives me matrix multiplication. So composition of functions maps to multiplication of the matrix derivatives. This leads us. Then this also lets you probe other things that you can express in terms of composition. So, for instance, maybe I have some high-dimensional space, and I have some surface in this space. I'm not sure the dimension of the surface, so like maybe I could be looking at a two-dimensional surface in 3D space, or maybe this thing is a line, but I'm not sure because like what I have is this space. What I have is some function that gives me x, y, z coordinates as some function of, let's say, t, u, and v. So like in principle, it could be up to 3-dimensional, but it could also be 2-dimensional, or it could be 1-dimensional. I don't know. Well, how can we check for that? The point, if it's 2-dimensional, then that means I can write it as a composition of a function with a 2D output. If it's 1-dimensional, that means I can write it as a composition of a function with a 1D output. And then the corresponding thing to check for over here is, can I find a matrix of dimension 2 or dimension 1 or whatever, such that the derivative, that the Jacobian of f with respect to x be written as like a product where one of the matrices is lower dimensional. So in other words, it's a low rank decomposition. So I can take a low rank decomposition of my matrix to check if it's parameterizing a lower dimensional surface. Now it's not a perfect check. It's a necessary condition, not a sufficient condition, but it's the like first pass thing you do if you want to check how high dimensional this surface is. So that's one example. Another example. What else can we do with functions? At least sometimes.
Add them.
Yeah, we can add functions. Sure, let's add functions. Assuming that simple outputs.
You can only sometimes add the two functions, though.
What's the corresponding matrix operation?
Addition.
Addition. Right. Yeah. And you know that works exactly the way you expect. What else?
All the other shit you do with vectors, spaces, or whatever.
You can multiply them.
Definitely multiply them. I'm not gonna do that one. I think that to be not that great. What else?
Invert them?
There we go. Invert them. That's an interesting one. Sometimes you can invert functions. What do you think that does to the corresponding matrix?
Inverts it sometimes.
Inverts it. Yeah. There we go.
Wait, is that true? If you take the derivative of f. Wait.
Yep.
I guess that. But if you take the derivative of f inverse, you get something weirder than that, though.
Nope.
Wait, really?
Would you like to see the argument?
It makes sense visually.
I remember I was reading a calculus textbook, and it was like inverses are weird.
In the calculus textbook, they sometimes look weird because they write it funny.
Oh.
So f of x plus dx is approximately x plus dx. All right. So how do we translate that into an inverse? Like, what would you do for an inverse? What's the key defining property of an inverse? You got y
Oh.
equals f inverse of x implies x equals f of y. So we take small changes, we get dy equals partial inverse x. On this side, we get dx equals partial f partial x, partial f partial y dy. The only way both of those equations can be true at the same time is if partial f inverse partial x partial f partial y. In other words, to get the derivative of the inverse function, you just take the inverse of the Jacobian. The reason it looks funny in your calculus textbooks is that they would have written this as something like partial f partial y evaluated at y of x, because f inverse is a function of y, not of x. So, like, in order to make it a function of x, you then have to calculate y of x.
I feel like there's a weird in that.
But yeah. What else do we like to do with functions? Today we talked about wedge products, which you can sort of view in this way if you want to talk about like volume elements. I'm not going to write that one up because it's confusing. Here's an interesting property of functions: symmetry. So, for instance, maybe I've got some f of x, y. For any f of x and y, it's equal to f of y, x. Right? That's symmetry. What would be the corresponding matrix property?
Symmetry?
Not symmetry in the usual sense of symmetric matrices, but symmetry in this sense. You can do a permutation like this. So swap around which one's the x and which one's the y. Like, maybe that should be on this side. Yeah, that's the idea there. Okay. Other interesting properties. So this would tie into what we talked about in the last lecture, where like if you have systems that are symmetric under these sorts of permutation operations, then you can leverage that to get a bunch of information about their eigenvectors. And like the place where those symmetries come from ultimately is there's some symmetry in the underlying functions. Another thing you might want to do with some functions, we talked about elimination. So maybe we have a set of equations, f of x equals 0, g of x, f of x and y equals 0, g of x and y equals 0. And then we want to do something like use this equation to eliminate the y. So do something like conceptually y equals g inverse of x, and then plug that in over here to get f of x g inverse of x equals 0. Something along those lines. All right, and then corresponding matrix operation.
Sure, complement stuff.
Sure, complement. Yeah, there you go. So complement, so you've got your matrix A, B, C, D, and then you get the matrix, which is effectively these equations eliminating these variables, A minus B inverse C. 2, 3 more. Oh, mutativity, that's an easy one. So, for instance, maybe I have f of g of x is equal to g of f of x for all x. Would be the corresponding matrix operation.
Commutative matrices.
Commutative matrices, yeah. So I'm going to get I guess I would write it as, there's not a very good notation for this. Let's say partial f, partial whatever the input to f is. I'm going to call the input to f y for now. G partial x is equal to partial g partial y. Yeah, it's not great notation, but the point is you've got like you're gonna get the same two matrices. Okay. Anyway, and I'm just embarrassed about notation now. Whatever. We'll leave it. Then last one, sparsity. This one you more often see in the matrix case before you see it in the function case. So we've got a matrix that has like a few non-zero elements in it, and then a whole bunch of zeros. Right? What does this correspond to in the function case?
Oh, where the value of a function is only determined by a few points.
There you go. So we've got, like, for instance, a system of equations where maybe the first function only depends on x1 and x20.
Mm.
And then maybe the value of the second function only depends on x5 and x19, and so forth. So you have sparse dependence yields a sparse matrix.
Wait, so in the function case, this just means that you can define the function for, I don't know, n points using only like some small k points.
Say that again?
Like you can define the function f for any amount of points using only a bunch of points.
Yeah, so example of this would be if I'm simulating a bridge and I'm thinking about the force on this particular node on my truss bridge, that's only going to depend on the tension or compression in like the struts that are immediately touching it. It's not going to depend on the tension and compression in any of the other struts. So it's only going to depend on like what, 3 or 4 or half a dozen of the x's, and then the rest of them are just not going to be.
Yeah.
You were also right about the invert thing. My brain was getting confused about the two meanings of invert here, and wasn't like casting that the right hand invert correctly to
Oh, that makes
the scalar
sense.
case.
That's everything on my list. Yeah, that's everything on my list. So like the broad takeaway here is, as a general rule, when you're thinking about some function or some system of equations that has some structure to it, you can usually think about either exploiting that structure or probing that structure by linearizing. So for instance, maybe I want to ask a question like, for instance, we were asking that thing about does this function encode a low-dimensional surface? I can design a linear probe for that by looking at the corresponding matrix operation. Or if I want to ask a question like, do I have sparse dependence in these functions? I can design a probe for that where like I differentiate and then look at sparsity of the matrix. And you may need to do some of this stuff along the way. Like maybe sometimes my hypothesis is that there's some nice structure to the inverse function, or some nice structure to some equations after I've eliminated part of them, right? And then, you have to do these operations and then do the appropriate probe. But like the overall point here is that this is sort of a strategy for probing the structure of a system. You have some system, you want to know what sort of internal structure it has, so like you linearize and then you set up your hypothesis in terms of some function structure, translate that to the linear case, and then you can probe your matrix to see if it has the corresponding matrix structure. That's it. That's the linear algebra series. Thank you for coming. Any last questions? Okay, guys.